Okay, so we're going to talk about induction. So before, we were talking about Faraday's law. Where the electromotive force, that minus sign just gives us the direction, but yeah, it's equal to the change in flux over some, like the rate of change of flux. And we're looking at this more practical version of Faraday's law. There's another form where we write this as integral of E dot dl to relate the electric field to the magnetic field a little more directly. But here we're talking about circuits. So let's say, for an example, say we have a circuit like this, where we have a switch and just a resistor. Now, let's say we plot the current as a function of time. And let's say we throw the switch at this point here. We can apply the loop rule. Let's say that at this time we close the switch. And if we apply the loop rule, we draw this loop here, and we have E minus IR equals 0, where E is the EMF provided by the battery. And so we get I is the EMF over the resistance. And so what this is implying is when we close the switch, the current goes from 0 to epsilon over R. So based on what we learned before, we have this instantaneous jump in current, which we know is not physically realistic. And now we can see that this is not what's going to happen in reality, because once we create a current, that's going to create a magnetic field. So we have this, this loop here, which encloses an area. And once we create a current, so we close the switch. So there's going to be a magnetic field in the loop. So the flux initially is 0, but now that we have a change in flux, now we can fix our loop rule. We have the EMF of the battery. Let's call that B for battery. Plus the EMF due to Faraday's law. Actually, I don't want to call that B because that could also, let's just say, here. So now we have the EMF of the battery, but now since there's a changing magnetic field, there's going to be this additional term. And, oh yeah. Now, in theory, we could solve this equation. But this term here is going to slow the, like if we look at this instantaneous jump, that would make this term infinite, which clearly can't happen. So, but we're going to get a very rapid change in current initially. So there's going to be a very significant back EMF that tries to oppose that rapid change in current. Because as the current changes, the magnetic field increases. And so we'd have this rather rapidly increasing flux in our loop. And so what's going to happen in reality, we close the switch here, and we're going to get something that looks like this. Again, for a circuit like this is going to happen extremely quickly, just not instantaneously. Now, in theory, we could calculate this by writing what the flux is. But that's where we kind of run into a problem. So we're applying the loop rule here to that loop. And we would need to know the magnetic field. And that's the part that's tricky because it's going to be different at different parts in here. We'd have to use a Biot-Savart law for this rectangle. And again, we don't want to do that. So in theory, it's possible. But yeah, we're not going to actually do it. But what we're going to do is we're going to say that the flux in this loop, well, first, let's say that the magnetic field in our loop, so again, we just have this area here, that's proportional to the current. And so, so if we look at d phi dt, we have a constant area here. And so d phi dt should be proportional to the rate of change of current. And again, that's true as long as we have a constant area, that the rate of change of flux is proportional to the rate of change of current. And so, and this is d phi dt is the EMF. So the EMF is proportional to the rate of change of current. And again, that just makes sense. If the current is changing very rapidly, you'd have a rapidly changing magnetic field, rapidly changing flux, large EMF. And so to turn a proportionality constant or a proportionality relation into an equation, we have to introduce a constant. And we call that L for self-inductance. And so now we can write this equation here. So E is minus L pi dt. Sometimes you'll see it without the minus sign. Yeah, let's just forget the minus sign. We're looking at the magnitude of the EMF. That's proportional to di dt. L is the proportionality constant, and then it's called the inductance. And inductance is measured in a unit called a Henry. Usually for inductors, we use like millihenries or micro or something, but that's the basic SI unit, the Henry. And from this equation, we can see that a volt times a second is a Henry times an amp. You just like multiply by dt, volt times a second, Henry times an amp. Okay. So now generally finding L for a case like this would be rather difficult. And again, we're not going to do it for this, but one type of device where we're actually going to find the inductance for two different devices. One is a solenoid, and another one we can calculate the inductance is a toric. Those are nice kind of simple shapes where, like for a solenoid, the magnetic field is just along the axis of the solenoid. Now, of course, it spreads out when you get near the edges, but basically the magnetic fields are going to look like this. So to a very good approximation, when you're inside the solenoid, the field lines are parallel to the axis of the solenoid or perpendicular to each loop. And so we can say that for a solenoid, to a pretty good approximation, the flux through a single loop is going to be that magnetic field times the area of that loop. So again, here's a solenoid. So the area would just be this cross section here. So, so let's calculate the inductance of a solenoid. We'll start with that. I'm going to leave this picture here. So let's say we have a solenoid of length L. Now I'm going to use a lowercase L because capital L is self-inductance. Now, at this point, you might wonder why I keep calling it self-inductance. Later, we're going to talk about something called mutual inductance as well. And just real briefly, say we have a situation like this, where we have one coil here, and then another coil right next to it. So like if, say we put another solenoid here, well, there's going to be a magnetic field, like say we're powering this one. We have a current here, that's going to create a magnetic field at the location of the other solenoid. And so if we change this current, we're going to create a flux. We're going to change the flux in this coil, and that'll actually drive a current in this coil. So there can be nothing between these two except a vacuum. And so we have a current in one that can create a current in the other just through Faraday's law. The changing fields can drive a current in the second coil. And so that's called mutual induction, but that's a separate topic. So L is for self-inductance. This would be mutual inductance. So to start off, well, we can look at Faraday's law. And let's say phi is the flux, through the solenoid. And to a good approximation, we can say that's equal to N times phi 1, where phi 1 is the flux through a single coil. So we're assuming the same flux through each coil. So if we have N coils, we just find the flux through a single coil, multiply by the number of coils, or number of turns in it. And yeah, it might not be true for the edges when things spread out. An alternative way of looking at it is just say phi 1 is the average flux for each coil. But yeah, so then if we look at Faraday's law, the EMF is equal to d phi dt we can take the N out. So EMF is the number of loops times the rate of change of flux in a single coil. And let's compare that to this other. Here we have E is L di dt. So we're going to say that this inductor has an inductance L. And so the EMF across the inductor is an L di dt. So let's set these equal to each other. Now, if we integrate with respect to time, we can simplify this. Where N times the flux through a single coil is equal to Li. So just by integrating with respect to time, what we'd have is N times the integral of d phi 1 would be L times the integral of di. So like we have d phi 1 dt, we integrate it with respect to t, the dt's kind of cancel out. As long as there's no mathematicians around, we can say things like that. But also we have to recognize that when the current is 0, then the flux is 0. So that's why it works out without it, we're integrating. So there's a possibility that there'd be like a plus C somewhere in there. But when there's no current, there's not going to be a flux either. So both of these are 0. Then we go to our final current and get our final phi 1. And so this works out. So we can say for a situation like this, that the inductance is going to be N phi 1 over I. Now, there's something I mentioned earlier that's going to show up here, which is very important. What happens if say to find the inductance, we have to have some current in there. What happens if we double the current? Is the inductance going to be affected? Or if we triple the current or change it in any way? And no, it looks like L should be a constant because let's look at for a solenoid. For a solenoid, I'm going to write it this way. The magnetic field for a solenoid is mu naught Ni over L. And so if we say double the current, we're going to double the magnetic field. The area is constant. So if we double the current, we double the magnetic field, which means we double this flux. So we'll have a factor of 2 in front of here and a factor of 2 here, and they're going to cancel out. So our inductance will be constant. So we can talk about the inductance of a solenoid. That does not depend on the current. It's kind of like what we talked about before with capacitors. Like everything about it depends on how much charge there is, except the capacitance. That purely depends on geometry. And we should expect the same for inductance. But let's check it out. Okay. So I think we have everything we need. I'm going to erase all of this. Let's actually calculate the inductance. So we just have to put things together. Let's start with phi 1. That's a flux through a single coil, which is a magnetic field times the area. So the area is this cross-section area. So if you picture you have like a cylinder and you wrap your wire around it, then A would just be that cross-section of the cylinder. And if we plug in the magnetic field for a solenoid, lowercase l, because we're dealing with, we reserved uppercase L for inductance. We don't want to get those confused. And now it's kind of a very simple matter. Just plug that into L. The inductance of our solenoid, the solenoid, we have N times, let's write it as N times phi 1 over I. So phi 1 over I, we just get rid of that. So we have mu naught N squared A over L, where N is the number of turns in the solenoid. I think we did that for this one. I don't remember the number, but you literally just count the number of turns. I didn't count along the entire thing. They're very closely spaced together, so kind of like right next to each other and pretty thin wires. So I never bothered actually counting the full thing, but you can count for like 1 centimeter, then multiply by the length. So that's the inductance for a solenoid. This is one way we can write it. Now, another way we can write it, you might see either way. Remember, lowercase n is the turns ratio. That'd be the total number of turns per length. And so if we just, big N is little n times L. So if we replace that with N squared, L squared, we get rid of that L in the denominator, have 1 in the numerator. And we can see that, two ways of writing the inductance of a solenoid. And this depends purely on geometry. Mu naught, let's write that down somewhere. So that's a constant, but otherwise it depends on like the number of loops, the area, and the length of the solenoid. And what's kind of interesting as well, Notice that A times L, that is the volume of the solenoid. So that's kind of interesting as well. Later on, we're going to talk about energy as well. So these magnetic fields, we're going to say that they store energy as well, just like electric fields. If you want to charge up a capacitor, you have to put energy into it. Or alternatively, if you discharge a capacitor, it's going to release energy, which you could turn into work. You could use it to, at least for a short time, light up a light bulb, for instance. Or I think there was an example that I showed a picture where you had that there's a huge number of capacitors, and they were designed to release all their energy to power a laser, just for like a quick pulse. But yeah, and you can get that energy back. And the same thing with solenoids. So when you charge up a capacitor, they store energy. We say that energy is stored in the electric fields. Similarly for inductors. We're going to talk about that a little bit later. So we have the inductance of a solenoid. So any questions on that? Again, measured in units called henries. Now there's one other device we can find. I'm going to write just one version for a solenoid. So the inductance of a solenoid, and again, maybe we should actually calculate that. Let's do a rough calculation and find the inductance of this solenoid. So I'm going to have to, I don't even have a way to measure it exactly. So I'm just going to guess. I'm going to say that the length is 10 centimeters. Let's say the diameter is 1 centimeter. So we can get the area from that. Now I need the turns ratio, which I'm just going to estimate. So let's see. Let's say there's 14 turns per centimeter. That's pretty reasonable for this object here. So let's find the inductance of this solenoid. So I think it's a little longer. 10 centimeters. Let's see, that's 4 inches. This is more than that. Let's say 15 centimeters. That seems fairly reasonable. So let's find the inductance. And really, it's just a matter of plugging things in and getting the units to work out. So the inductance, I'm going to write it here in case I need the whole board going across. I'm actually going to write it this way. 4 pi over 10 to the 7 Tesla meters over 10 to the 7 amps, because we're going to have the area is going to have a pi as well. Actually, we're going to be multiplying by that, so never mind. Now we get some cancellation, but so in other ways, 1.26 times 10 to the minus 6 Tesla meters per amps. N squared, 14 squared is 196. That's one of those, just knowing the squares of numbers kind of useful. And that'd be per centimeter squared. The length is 15 centimeters, so we get rid of one of those. And then let's throw this conversion factor. 100 centimeters is a meter. And then we have to multiply by the area, which would be pi d squared over 4. So it's pi r squared, but r is d over 2. So pi over 4 times d squared, 1 centimeter. We'll write like that. I guess we didn't need this conversion factor entirely. But yeah, that's fine. All right, now let's check the units. We should get a volt here. I think if we use this, volt, or we should get henries here. So let's say a henry times an amp is a volt times a second. We have to get rid of Teslas. So let's do that. A coulomb times a meter times a Tesla is a Newton times a second. And a coulomb times a volt is a Newton times a meter. So let's just check the units and see if this is going to work out. I can do that up here. Teslas times meters. I'm going to write centimeters squared. Meters squared. Henries. Amps. Newton. Seconds. Coulombs. And volts. On the bottom, we have amps. Centimeters squared, meters, volts and seconds, coulomb, meter, Tesla, and a Newton times a meter. So yeah, it looks like it actually worked out. This will give us our inductance in henries. So if we divide by a henry, the inductance in henries, we have 1.26 times 196 times 15, throw a pi in there, and then times 100. So let's just double check. Okay, now on the bottom, we have 4 times 10 to the 4th. Just going to do that. Okay, so let's let's do this. See what we get. So I'm getting the inductance here. Oh. I thought that was kind of high. Forgot one thing. In our constant, we had 10 to the 6 in the denominator. So that's a factor of micro. So let's just convert to microhenries. That's a much more reasonable value. So the inductance is 29 microhenries. Okay, so that's about the inductance of this thing. And so if we had a circuit with this and a resistor, or this has its own resistance, so we wouldn't necessarily even need a separate resistor. If you flip a switch, there will be like a back EMF in this case, where theoretically that exists for a just a regular circuit without an inductor like this, just because we have a current that has to be a loop. Current has to go through a cycle, so it absolutely has to form a loop, and there will be a magnetic field in that loop. So generally speaking, there's going to be inductance in every circuit, but you can kind of cancel it out by wiring things so they form loops kind of in opposite directions, so they cancel each other out. But generally speaking, every loop So every circuit is going to have some inductance, but usually extremely small. This would be much higher than a regular loop. Still, it would be hard to actually see a time delay. If you, flip a switch without something like an inductor, like a solenoid in it, or with a solenoid in it, it's still hard to just see it visually. Like if you have an amp meter and just watch the numbers go up, you need a very large inductance to notice it. And we will talk about that in more detail a little bit later. But are there any questions on self-inductance so far? Or you think of inductance as like a form of, as a kind of like inertia for a circuit. So if you have a circuit with a solenoid in it, you flip a switch, you're building up a current. This is going to fight that. It wants to keep that current from happening. So the current will build up more slowly. Alternatively, if you close the switch in a way where you still have like a full loop, the current wants to drop to zero now, but this is going to prevent it from immediately dropping. It wants to prevent any change in the current. All right, now there's one other case. A solenoid is a nice device because we can calculate relatively easily, but another device where we can calculate the inductance is a toric. We're going to do specifically a rectangular toric just to make life easier. So it's kind of similar to the problem that we did before, like last class. So here, let's look at a toroid from two perspectives. We have a top view. And that forms these magnetic fields that loop around. They'll give it a direction. The direction, of course, depends on the direction of the current, but we don't care what direction it is. And so basically, it's like a donut-shaped thing. You have one wire just wrapped around over and over again. And if you look at us, we can easily find the magnetic field inside by applying Ampere's law. So I say easily, but again, you always want to be careful with Ampere's law because we have that integral. So this is a dot product, but in this case, we pick a circular loop, and because the magnetic field lines are circular, we can get rid of this dot product. B dot ds is just equal to B times ds. So that's one great simplification. And another one is we can take the B out of the integral. Now, let's say I is the total current through the surface formed by that loop. We have a current lowercase I in the wire. And if there's n turns, like say the wire comes out and then loops around and goes in. So it's crossing our surface only on the inside. It doesn't, when it comes out here, that's not in the surface. So every loop, it's going to go into the surface, but it's not going to come back out inside the loop. If we drew a loop outside here, then the total current inside would be zero, because every time it comes out, it goes back in. So the net current would be zero in that case. So if I is the current in the wire, we have B times the integral of ds as mu naught n I. And that integral of ds is just the circumference of that circle. We're going to move this down a little bit. Okay, so that's a magnetic field at a given radius. Very easy to find with Ampere's law. Okay, now like here's the center of the torrid. And again, we're going to do a rectangular one just because it'll be easier to calculate, because a magnetic field depends on the radius. So if we look at the side view, like here, the torrid is going into the board, looping around and coming out. And so the way I drew it, we have a magnetic field here going into the board. On this side, it's coming out. So this is a magnetic field line looping around, goes in, comes out. And now the magnetic field is not constant inside this cross section. So like, again, we're going to use the same formula to find the inductance. So in this case, the flux, phi1 is the flux through like a single cross section. And so we have to find out what that is. And so to find the flux, let's do that. We have the integral of b dot dA. So we're going to have to integrate this, but it's actually going to be a kind of a trivial integral. It's one we did yesterday, actually. Or not yesterday, but Monday. So let's say that this has a height h, an inner radius of a, and an outer radius of b. So we have to have the dimensions of the torrid, and it doesn't have to be a square. So like the width here is b minus a, height is h. And let's actually just find the flux through this rectangle. Let's call that d phi 1. That would just be b, because the magnetic field is constant everywhere in that rectangle. So we'd have b times h dr. Just magnetic field times area. Because the fields are looping around, like here it's going into the board. And yeah, it's like constant everywhere on that rectangle. And it's perpendicular to the cross section there. So again, the flux involves a dot product, but it works out very nicely in this case. And we can plug in our value for B. I'm going to do it like this. So I think we've got everything. So we have B times H dr. So B is mu naught Ni over 2 pi r, and then times H dr. So that looks good. What I've done here is isolate a constant times, the parts involving r. So like mu naught is a constant, number of turns is a constant. Current doesn't matter because we're going to divide by the current. But say for any fixed current, H is a constant, and of course pi is a constant. Pretty sure 2 is still a constant. So now to find the total flux through this cross section, now we just have to integrate over r. So we take our constant out. And then we integrate dr over r from A to B. And I'm just going to write down the results here. So the integral of dr over r is the natural log of r. So we have the natural log of r evaluated between A and B. So it'd be natural log B minus natural log of A, which is ln B over A. So now we can find the inductance very easily then. We have, basically we just take n. So if we take phi 1 divided by I, we just get rid of that I. and now we have a constant, and then we multiply by n. Let's actually write this down here, the inductance for a torque. So we divide by I, so just picture that's gone, then we multiply by n, so we have mu naught n squared h over 2 pi times the natural log of b over a. So that's the inductance for a torque. And again, in order to calculate the inductance, you need to be able to find that flux through, like overall through your device. And that's not always easy to do, like especially in an analytic way. With computers, you can always do things numerically, but to actually calculate it, just like on the board, that can be a pretty complicated thing. And there's only a few shapes we can do that for, so why don't we do that? So we did that for a solenoid and for a torque. All right, so are there any questions on any of this so far? Okay, so let's look at circuits with inductance. So I'm going to stop the recording and then start it again. Let me erase this first. I'll leave that for now. So let's draw a circuit first. Okay, so here is a circuit. Now we use this symbol for resistors. The symbol for inductor is this kind of, looks kind of similar, but it's curvy lines instead of these jagged lines for a resistor. And I think the reason they use that symbol for an inductor is because it's basically a solenoid. And yeah, so we can actually build the circuit like this very easily. This is a switch. We can throw the switch to position A, and now we have this closed loop with a battery, the resistor, inductor, and it's a closed loop. It goes back to the negative terminal of the battery. And if we throw the switch to B, we have this loop just involving the resistor and the inductor. And there's just if we didn't actually have an inductor in a circuit, or we could have something without a resistor as well. Let's say I just hook this up to a battery. So we have nothing except a battery, which hooks up to this inductor, the solenoid. This would, okay, fine, a switch too. But this would be a good representation of that because there is resistance in our circuit. So like the resistance would mostly be in the solenoid itself, but again, you can draw those separately. Or just like if we didn't have a resistor at all. If we just had a battery connected to a resistor, there is some inductance just in the loop itself. And so we can represent the inductance of the solenoid by just placing it here. You can just draw it anywhere you want. Now, there's something that I'm still teaching this the way that I learned it and the way that all the books present it. But I've kind of been thinking about it recently because I saw there's a guy at MIT who has these sequence of lectures that are, very good. And he hates this kind of argument here, or this kind of analysis here. And the reason he hates it. He thinks it's nonsense. Like we can talk about a voltage drop across a resistor, that's fine. But what about a voltage drop across an inductor? He doesn't like that because, or the idea of voltage, we came up with that by noticing it's that electric fields are conservative. But if we go to this case now, where we have an inductor, when we talked about that last time, these are not conservative any longer. And so, yeah, I'm kind of rethinking how I teach that, but for now, I'm just going with what your book says and everything else. But it's actually, maybe I'll even put a link to this MIT lecture where he talks quite a bit about this. And we're going to do it the traditional way, even though there's maybe an asterisk there about whether or not it's even valid. But we're going to get an equation. And we can get the exact same equation just using Faraday's law. But let's just kind of stick to the simple, we say there's a voltage drop across the inductor. So again, that's a little questionable to say that, even though it works in practice. And we can get the exact same result without saying that. But mainly for what we're going to talk about in the next chapter, it's kind of useful to have this idea of a voltage drop across an inductor. But anyways, let's, so we're going to apply our loop rule. Let's say we throw the switch to position A, and then let's apply our loop rule to this outer loop here. We have a closed loop that involves a battery, a resistor, and an inductor. And we know ultimately what's going to happen is we're going to get a current equal to, well, here, I'm going to write I max. That's what we get with no inductance, and that's what we're going to get ultimately with the inductor as well. That's not going to affect the final current that we're going to get in the circuit. And the reason is when we close the switch, initially the current is 0. So when we close the switch, now we're going to start building up a current. And when we do that, we're going to get this back EMF. And, but as the current grows, it's eventually going to settle down. I mean, the current is going to grow, but it has to stop at this value. You know, it's going to be slowing down. And as it slows down, the voltage across this inductor is going to decrease. Because remember, the voltage across the inductor, it's related how quickly the current is changing. And so initially we're going to get kind of a, the current's going to rise, but it's going to level off. And when it does that, the rate of change of current is going to slow down. And so this back EMF, it's initially going to be very large, but then it's going to settle down. And eventually we'll get a steady current. So once we have a steady current, this will no longer be a factor. So we're going to get the same ultimate result. The inductor should just give us a time delay. And we want to see like what kind of time delay we're talking about. How is this current going to grow with time? So that's what we want to do. Solve the current as a function of time. So let's look at our loop rule. So battery, we have E, the EMF. Then we have a voltage drop across the resistor. And a voltage drop across the inductor, which is L di dt. And we've completed our loop, so that sum has to equal 0. And this is a differential equation, which we want to solve. So first off, I'm going to rewrite it. So if we just move this term to the other side, we have L di dt is equal to epsilon minus IR. And this is actually not a very difficult equation to solve because this is what they call a separable equation. So we can rewrite this. If we divide by epsilon minus IR, and then multiply by dt. So if we divide by epsilon minus IR, on this side we have 1. We move that dt over. Again, we're not literally multiplying by dt, but we can rewrite it this way. Now this is in a form where we can actually integrate both sides. So just kind of a simple rewriting of the differential equation. It's into a form that we can actually solve. And regardless of how it looks, this is not so bad. This is basically something like dx over x, because our variable is I. So if we forget about that term for a minute, it looks like we have like di over I. A constant isn't really a big deal. Here we have a constant in front, which we have epsilon minus IR. But again, we can easily deal with that with a u substitution. So basically, this integral is a lot like dx over x. So we should expect a natural logarithm as a result. But let's integrate both sides. Now, notice at t equals 0, there's no current. So on the left side, we're integrating over t. So t equals 0, the current equals 0. Let's put primes here. We integrate to some maximum. At some time t, we have a current I. And the integral on the right is incredibly trivial. The integral of dt is just t, and we evaluate that between 0 and t. So we have t minus 0, or just t. Now we have to play around with the left side. So are there any questions on getting this set up? Okay, so let's make a u substitution. Let's say u is equal to epsilon minus I prime r. And again, I'm just calling it prime because you don't want your variable of integration to equal one of the limits of integration. That's not really a big deal. Sometimes I even ignore it, but they were kind of making a little change of variable in here, just replacing I with I prime to distinguish it between that limit. If it's a variable here, then don't want it to be, we don't, this here is just a number with a unit. It's not a variable. So yeah, u equals that, then du is minus r di prime. Okay, now we want to change our limits as well. From 0 to I, that's where we're looking at the current, but now we're looking at a new variable. So let's do this. Let's divide by r and multiply by r. So here, like we can put, let's take this minus sign out, or forget about this minus sign for now. We have an L here, so let's multiply and divide by r. So now RDI, or RDI prime, is equal to minus du. And on the bottom, we just have u. And that's equal to t. But now we have to change the limits of integration. So here, when I prime is 0, u is equal to epsilon. And then when I prime is equal to I, u is just epsilon minus IR. And we're almost done here. Let's pause this for a moment. And let's look at L over R. Let's look at the units. We have henries over ohms. So we know a volt times a second is a henry times an amp. And a volt is an amp times an ohm. And yeah, I think that's it. Let's just cross off. Here's our ohms, henries, amps, and volts. So a henry over an ohm is equal to a second. And so we're going to give this name, a name. We're going to call that the time constant. So tau is equal to L over R. So just like for the case with an RC circuit where we had a resistor and a capacitor, we defined a time constant for a capacitor, where tau equals RC. Here for this inductor circuit, we have a different time constant equal to L over R. Okay, so let's make that substitution. So we have minus tau, that's that. And now the integral of du over u is the natural log of u. So we have the natural log of this value minus the natural log of that value, which is the natural log of epsilon minus IR over epsilon. And that's equal to t. So we're almost done. We want to solve this for I. But any questions up to here? All right, so I'm going to divide by minus tau. So natural logarithm of epsilon minus IR over epsilon is minus t over tau. And we can undo this just from like the definition of like how logarithms and exponentials are related to each other. So this epsilon minus IR over epsilon is e to the minus t over tau. So, we have natural log of something equals something else. That means e to this power equals that. So e to the minus t over tau equals what's in the logarithm. And we basically just want to solve for the current, kind of out of room here. So I'm going to erase some things here. Let's just write the result. If we solve for I, we have IR equals, let's divide by R. Let's divide everything. Here, let's do this. I'll do it in 2 steps. And then if we divide by R, we can write it this way. So that's our final answer. For current as a function of time, we start out at a current of 0. We should probably check that. Let's say t equals 0. Then this term, we have e to the 0. So e to the 0 is 1. So 1 minus e to the 0 is 0. And we do get a current of 0 at t equals 0. And if we take the limit that t goes to infinity of the current, and when t is large, we have e to the minus t over tau. So if t is a large number, we're going to have like 1 over e to a large number, which is going to be very small. So for large times, we can say that this whole term is insignificant, and then we just get epsilon over r, which is our maximum current, which is what we said over here. Our I max is epsilon over r. So we could replace this with I max. So yeah, we start out with current of 0, and we're going to end up with a current epsilon over r. Let's see how long that would take. So let's do a quick problem. Let me erase a lot of things here. I should have kept the time constant. So for an inductor, the time constant is L over R. I think we can get rid of everything here then. Okay, so we plot the current as a function of time. We start out at 0, and we have to approach this value. And it's this exponential term here. So it's going to start out kind of growing rapidly, and then approach this limiting value. So we're plotting current as a function of time. So when we get to like large time values, not much is going on. It levels off. It's not changing very quickly. We can see like di dt is the slope. So it starts out with a large slope. And so that's, like here, di dt, it's a very steep slope. And so there's a large voltage drop across the inductor and a much smaller voltage drop across the resistor initially. So like in general, we can say that the EMF provided by the battery, that has to equal the voltage drop across the resistor plus the voltage across the inductor. And initially, there's no current in the resistor. So at t equals 0, there's no current. So at t equals 0, the voltage drop across the resistor is 0. And so the EMF, or the voltage across the inductor, is equal to the EMF of the battery. So if there's no current in the resistor, no voltage drop here, all of the entire voltage drop is across the inductor. And so, that's why we have this rapid increase in current initially. The voltage, the higher the EMF across the inductor is equal to the entire battery. That's the highest it can be. And so we get a rapid increase in current. And then, but now that we have this current building up, now there's a voltage drop across the resistor. And so, again, because these two have to add up to whatever the battery is, when the higher the current, the greater the voltage drop across the resistor, the smaller the voltage drop across the inductor. And so this di dt is smaller. The more current going through the resistor, or the more current going through the inductor, the smaller the change is going to be. All right, so let's use this as an example. I think we had 29 microhenries. So let's say L is 29 microhenries for this inductor. And let's say that, say we just took up something like this. let's say the resistance, let's say we don't actually put a resistance. So we just have the resistance of the solenoid itself plus whatever wires connected to the battery. Let's say the resistance is 11 milliohms. So first, let's calculate the time constant. So if we just took up a battery here with that inductance and not much resistance, let's start out by finding the time constant. So that's L over R. So it'd be 29, here, let's do henries over 10 to the 6 divided by 11 milliohms. So mill is 10 to the minus 3, so we'll put that on top. And then remember, a henry times an amp is a volt times a second, and a volt is an amp times an ohm. I mentioned to cram those in there, and those two should do it. So we get seconds here. But really, let's convert to milliseconds by multiplying by 1,000. So the time constant is going to be around 2.9 milliseconds. So if we just hook up this to a battery, flip the switch, the time constant is around 3 milliseconds. 29 over 11, I think that's 2.9. Oh, never mind. 2.6, I was a bit off. Oh yeah, that makes sense. 22 and 7 over 11. So yeah, 2.6 seems about right. And again, that's why I said if you were to wire this up with an ammeter here, and you flip the switch and just watch the ammeter, you're not going to see it rising slowly like you did in the capacitor lab. You could see it rising slowly with a large capacitor. In this case, that's not going to happen. You can't see things. Well, it's going to take several time constants to reach its maximum current, but even 10 time constants, that'd be 26 milliseconds or 0.03 seconds. So again, that's going to happen in a blink of an eye. So even with a fairly large solenoid, you're still not going to see a visual effect of this. But we can improve this by placing, say, iron inside this. So if you place, say you place an iron rod inside this cylinder, now that's going to greatly increase the flux because we'll magnetize the iron and make the magnetic field inside a lot stronger. It's kind of difficult to deal with though, because the relation between like the current and the magnetic field is not exactly linear when you put iron into it. But so we're not going to go into any detail there. But yeah, that will increase the inductance by placing iron, just like placing a dielectric in between the plates of a capacitor will increase the capacitance there. We can do that by placing a magnetic material inside the solenoid. But yeah, so let's kind of look at what we should expect for the current anyways. If we look at, say, one time constant, let's plot the current as a function of time. Okay, so current is a function of time. So at 0, the current is 0. And then let's look at what happens after one time constant. Let's find the maximum current. So say that EMF is 4 volts. So remember, the maximum current is epsilon over R. So we'd have 4 volts over 11 milliohms. So let's do that. We would have 364 amps. Yeah, we've got basically, well, we have a very small resistance, and that's why we have a large current. So let's hope our wires can handle that. Unlikely that they can, but just say it does. All right, so let's look at one time constant. So actually, maybe I want to kind of do this as a separate thing. If I can find room for it. So let's look at, I'll just write them here, like e to the minus 1, e to the minus 2, e to the minus, let's just do 4. That's all we have room to write down anyways. So basically this is like 1 over e to start with. This is about 0.37. All right. All right. And let's do e to the minus 2. It's about 0.14. And then e to the minus 3, 0.05. And then one more, e to the minus 4, 0.02. And let's do, on this column, let's do like 1 minus e to the, kind of making a mess of the board. So let's make a table here. Let's say that this is time. Say tau, 2 tau, 3 time constants. And 4 time constants. So in this column, we have e to the minus t over tau. And here we have 1 minus e to the minus t over tau. So this would be 0.63, 0.86, 0.95, and 0.98. Can really only fit 3 here without cramming it in too much. So let's look at our current as a function of time. So at 0, current is 0. After 1 time constant, we take our maximum, which is 364 amps, and 1 minus e to the minus t over tau, that's this column. So we do 364 times 0.63. So this is about 230 amps. And then after 2 time constants, we do 364 times 0.86. That's 313. And then after 3 time constants, we're at 0.95. That's about 346 amps. So you can see we're like after one time constant, you're 63% of the way to your maximum current. And then after two time constants, you're 86% of the way. After three time constants, you're 95%, and then 98 after four time constants. So basically, let's see. After 7.8 milliseconds, we're 95% of the way to our maximum current. It'd be like tau, 2 tau, 3 tau. Yeah, this board is horrible. Filled it up completely. But yeah, you can see it kind of rises quickly. In one time constant, we go from 0 to 63%. But like we're looking at the same increase in time over each of these intervals, but the change goes from, here we're going from 0 to 0.63. That's a change of 0.63. And then a change from here to here of 0.23. And then 0.9, and then 0.03, or 0.09, 0.03. So the change drops off pretty quickly. And after 3 or 4 time constants, you can basically say, you've reached your steady state, which is maximum current, which in this case would be 364 amps. All right. So any questions on that? Let's do one more thing with this circuit. I'm going to erase this. This board is kind of driving me insane at the moment with how cluttered it is. Let's get rid of all of this. Let's do one more thing here. And let's say we're at our maximum current. So we throw the switch to A, leave it for like 4 or 5 time constants at least, or even if we just leave it for a full second, that would be like 40 some time constants. We'd essentially have reached our steady current. And again, when we have a steady current, we're at our maximum current. I did erase these numbers. It was, here we have an EMF. The battery is 4 volts. The inductance was 29 microhenries. Resistance was 11 milliohms. And we calculated the time constant to be 2.6 milliseconds. So now, let's write down the maximum current. Again, we calculated that. I think that was 364 amps. So let's say we've reached that steady state. That's a very large current, which means there's going to be a pretty strong magnetic field in that solenoid. The magnetic flux through that solenoid is very large. However, the voltage drop across it is 0 because the flux is constant now. So what matters is how quickly that flux is changing, not what its actual value is. So now that we have like a steady current flowing in here, this inductor has no effect at all. We're at 364 amps and it's holding steady. And now let's flip the switch to position B. And so now we have the voltage across the resistor plus the voltage across the inductor. That equals 0 because we have a loop here with no power supply. So now our switch is in position B. So we have this loop here. We had our current going like this. And so you might be a little careful with the sign. The current's always going to be going clockwise. And so the voltage across the resistor, that's going to be minus IR. And now the voltage across the inductor, this is going to be positive, I believe. Let's just double check that. So now we have a large current, and the current is dropping now because we remove the power supply. And so the resistor is killing off that current. And so how is the inductor going to respond to that? It's going to resist that change. Remember Lenz's law. And so the EMF is going to keep driving the current in the same direction. So now it's like the inductor and the resistor are fighting each other. I'm going to go across and just. So that is our differential equation now. And we also have this initial condition that I0 is equal to, I don't want to write it down because again, just taking up space. But yeah, the initial current is I max. So welcome to the differential equation. We need to know that as well. So let's solve this equation. It's going to be very similar to what we had before. We have L di dt equals IR. We can rewrite that as L over R di over I equals dt. Let me just check that. Basically if we divide by IR, we have L di over IR, and then we move the dt to the other side. But now we have to be a little careful. Well, let's integrate and take the limit, put the limits in. So if we integrate dt, we're just going to get t. L over R is our time constant. So we have tau times the integral of di prime over I prime. And here, let's do this. Let's actually do this as an integral. So again, at t equals 0, our current is I max. And then this will just be the current at some later time. So now we can make a simple U substitution, or we don't even need to. It's just like dx over x type of thing. So we have tau times the natural log of basically, we have natural log of I minus natural log of I max. I always picture the movie company when I say that. So tau times that natural logarithm of I over I max is equal to t minus 0, or just t. And let's divide by tau. So let's see, natural log so I over I max equals e to the t over tau. I wrote minus just out of habit. That should be there. Wondering where that went. Oh, okay. I made a mistake in the beginning, and I did it in. Well, yeah, I made a mistake, and I did it in the worst way possible, right in the beginning. This should actually be negative. So I kind of thought it through, and said it's fighting and trying to drive the current in the same direction. So overall, that whole thing should have been positive, but di dt itself is negative because the current is decreasing. And so, yeah, if this term is negative, then the minus sign would cancel that out. So, like overall, this whole term is positive if we put the minus sign in front. So I kind of screwed it up right in the beginning. So there should be like minus signs everywhere. So always got to make a mistake right in the start. So let's just put a minus sign everywhere. And then we get the result. Kind of similar to what we had before. So when we start out with no current, we flip the switch to A, and the current rises up to its maximum value, epsilon over R. And in a short time, it'll reach its steady state of epsilon over R. And now once we're at our maximum current, which is epsilon over R, we flip the switch to B, and now the current decays according to this equation. It's this exponential decay. So at t equals 0, e to the 0 is 1, the current is just I max. And then, we just have exponential decay. As t increases, this term gets smaller and smaller. And again, after several time constants, our current will essentially be 0. Okay. So that's the this LR circuit. Are there any questions on this? And we're kind of going through this fairly quickly. Let's look ahead real quick. A couple more things. Maybe we won't finish this chapter today because we'll have 2 days next week. But we want to talk about energy in magnetic fields. That's important. That'll be the next topic. I want to talk about an LRC circuit as well. So we have a few more things to talk about. We're going to talk about energy next. Energy. So again, like say we flip the switch to A, the battery is providing energy, and the resistor is dissipating it, but some of the energy is going to go into the inductor itself. And we interpret that energy as being stored in the magnetic field. So just like we did that for the electric fields and capacitors, we want to do the same for inductors and magnetic fields. So I'm going to stop recording here. This will be a video by itself. Then we'll talk about energy in magnetic fields.